right, so one last section in chapter 13, and this has to do with probability. And you've been working with probabilities probably since elementary school, a lot in middle school, but we're just kind of wrapping this up. A lot of this is going to be review for you. So basically, we know that probability is a number associated with the likelihood that something is going to happen. All right, and we've looked at examples of experiments before where we toss a fair coin or rolling a die or picking a card at random. Okay, so these are all things that give us opportunities to look at the odds or the chances that something occurs. So here we have some vocabulary. So just so we are all on the same page, and especially because in this textbook they use these specific terms in directions. So a lot of times we just need to know, what are we looking for? So first of all, a probability model is the probability of each outcome in an experiment or in a situation. Okay, so every outcome that is possible in a given situation, if you have the probability of each one of those, that's a probability model. The sample space, and sometimes they denote that by the word or the letter S, is just the set of all possible outcomes. All right, so how are these different? This is a list of everything that can happen when an event occurs, and this is the probability of each member of this list. I'm going to use this SS for sample space. So this is a list of all the things that can happen, and this is the probability of each one of these things happening. And an outcome is just one result, one possible result. Of one trial. Okay, so an example would be, let's flip a coin, and outcome is tails. That's just what happened when I flipped the coin. The sample space would be heads or tails. And the probability model would be the probability of heads is 1/2 and the probability of tails is 1/2. All right, so that's the difference for each one of those. So down here we have a probability model, and this is just math notation for what I just set up here. All right, so I'm just going to write what I just said down. So let's say I flip one coin. All right, when I flip the coin, my sample space is heads or tails. Okay, my probability model is, I'm running out of ink there. The probability for heads is 1/2 and the probability for tails is 1/2. Okay, so that's the difference between what the sample space and the probability model is. Now, when you're looking at probability, probability is a number and it's between 0 and 1. So that's what this is saying here. Basically, probability is between 0 and 1. If the probability of something is 0, then it cannot happen. There's no way it can happen. If the probability of something is 1, it is certain to happen. But if it could happen, maybe, maybe not, it's a number in between 0 and 1. Okay, we can think of that as a percentage. Okay, the higher chances that something happens, the higher probability it is. Another thing that we notice here is probability is always positive. Doesn't make any sense to have a negative probability. Okay, lowest number is 0, highest number is 1. So in this first example, it says in a bag of M&Ms, the candies are colored red, green, blue, brown, yellow, and orange. Suppose a candy is drawn from the bag and the color is recorded. We've probably done this experiment before. The sample space of this experiment is the list of the colors that I just read, and determine which of these are probability models. Now, one thing I forgot to mention here, that in a probability model, the sum of all the probabilities, the sum of the probabilities of all the outcomes has to add up to 1. So in a probability model, notice up here, in my probability, if I add them together, I get 1 whole. And all probability models must add up to 1 whole. So if I look at this first box here, they want to know if it's a probability model. So I need to add up all of these values. Ugh, they're tiny. There we go. So if I add up 15 and 15, that's 30, or 0.30, plus 3, that's 0.60, 0.80, and 1 whole. So this is 1. All of my probabilities add up to 1, and they're all positive, so yes, this is a probability model. In part B, if I add these up, I have 3, 4, 5, and 4 is 9, 10, 11, 12. So this is 1.2, which does not equal 1, so this is no, it is not a probability model. All of my outcomes don't add up to 1. In the next one, if I notice, I have my green says I have a negative probability, so this is no. It is not a probability model. And the last example, if I add up all my probabilities, which are all positive or 0, I get 1. So basically, this is just a bag of yellow M&Ms. And yes, this is a probability model. All right. Zoom out. So in the next example, it says an experiment consists of rolling a fair die 1 time. A die is a cube, which each face having either a 1, 2, 3, 4, 5, or 6, and they ask us to construct a probability model for this experiment. So first of all, we need to know what is in the sample space. Okay, in my sample space, I have a 1, a 2, a 3, 4, a 5, or a 6. That's my sample space. So my probability model is the probability of each one of these happening. So if I have the probability of rolling a 1 on a fair die, it's 1 out of 6. The probability of rolling a 2 is 1 out of 6. The probability of rolling a 3 is 1 out of 6. The probability of 4 is 1 out of 6. The probability of 5 is 1 out of 6. And the probability of rolling a 6 is 1 out of 6. All right, so I have each element of my sample space and the probability for each one of them. And if I were to add these up, this is 6, 6, so that adds up to be 1 whole. In example 3, an experiment consists of tossing a coin. This coin is weighted. Okay, so it's not a fair coin. It doesn't have equally likely outcomes. So the coin is weighted so that heads is 3 times as likely to occur than tails. All right, so in my sample space, I'm just going to call it S this time for sample space, I can get a head or a tail. So my probability model now, if I think about this, my chances of getting a head are 3 times as getting a tail. So if I say the probability of getting a tail is X, the probability of getting a head is 3X. But I know that these have to add up to 1, so X plus 3X equals 1. So 4X is 1 and X is 1/4. So the probability of getting a tail is 1/4, and the probability of getting a head is 3 times 1/4, or 3/4. And again, if I add these up, I'm going to get 1 whole. All right, so now we're looking at probabilities of equally likely outcomes. Okay, flipping a coin, rolling a die, everything has the same chances of happening. Okay, so to find the probability of that event occurring, we need to know how many ways can the event occur out of the number possible ways. Okay, so we're looking at equally likely outcomes. All right, so an example for this is and we've done this before, I'm sure you've done this before, calculate the probability that in a 3-child family there are 2 boys and 1 girl. Assume equally likely outcomes. That means the probability of getting a boy is the same as the probability of getting a girl. So in my sample space, I'm going to have, let's say I have a family where all of the kids are boys. Okay, so if the first 2 are boys, my third one could be a girl. Boy, boy, girl. Then I could say I have a boy first, and then I have a girl. Then I have a boy, or I can have a girl. How about, let's say I have a girl first. If I have a girl first, I can have a boy second, and I can have a boy or a girl for my third child. Or I can have a girl first and second, and then have a boy, and the third child could be a girl. So this is just an organized way of listing all the things that can happen in my sample space. But I need to know And by the way, if I count how many things are happening here, I have the total possible number of outcomes is 8. And I also need to know which of these has 2 boys and 1 girl. So I'm looking for 2 boys and 1 girl. Boy, boy, girl. Boy, boy, girl. So here, the number of favorable outcomes, or the number of ways that I can get 2 boys and 1 girl, is 3. All right, so I would say that the probability of getting 2 boys and 1 girl is 3 out of the total number, 3 out of the total number is 8. All right, so equally likely things happening. So then in example 5, it says to consider the experiment of rolling a single fair die. E represents the event roll an odd number. Now, if I listed all the things that can happen in E, I can have a 1, a 3, or a 5. Okay, so this is writing that event E. Now F, I can have a 1 or a 2. So these are my sample spaces for E and F. So I want to know now what is the event, or what would be in my sample space if I have E and F. Remember, this is an and. So if I put E and F together, E and F, I'm going to have a 1, a 3, a 5, and the 1 is already there, but a 2. 1, 2, 3, and 5. So there's actually, oh, I misread this. This actually is an or. So what I did, I got these mixed up. This is the union of E and F. So 1, 3, 5, and 2 is a list of all the elements in E or F. If I have E and F, it's the element that is in both groups, and the only one that's in both of them is 1. So this has 1 item, and this has 4 items in the set. There's just a set of 1, this is a set of 4. Then it says to compute the probability of E. Now, the probability of E is the number of odd numbers that we have, which are 3 out of 6 total outcomes. So if I roll a die, I can get a 1, a 2, a 3, a 4, a 5, or a 6. If I want the probability of it being odd, I count how many odds there are, which is 3 out of 6, which is 1/2. So the probability that F occurs, rolling a 1 or a 2, there's 2 things here out of 6, which is 1/3. Okay, so this is part C. In part D, I want the probability of E and F occurring. So probability of E and F. Now, there were only one possible outcome that works out of the 6 total. So that would be 1/6. And for part E, I want the probability of E or F happening. And if I go back here, I have 4 things in my sample space out of 6 possible outcomes. Okay, example 6 says the probability of E is 0.2, the probability of F happening is 0.3, and the probability of E and F happening is 0.1. So they're asking us to find the probability of E and, or F. Now we did some counting things like this back in section 1. Okay, these were things that weren't mutually exclusive. So what this means is I can add the probabilities of E and F happening, but some of them are in both sets. So I have to take away the overlap. Okay, so the probability that they're in both sets is 0.1. So I can't count them in both sets. I can only count them in one. So I have the probability of E is 0.2. The probability of F is 0.3 minus the probability that they're in both of them, which is 0.1. So this is 0.4. 0.4 is the probability that they're in one or the other set. Okay, we were looking at this with the Venn diagrams. And this is where we had to subtract the overlap. Now, if events are mutually exclusive, there is no overlap. Okay, so I can just add the probabilities together. Okay, so there's no overlap to take away. So if I have the probability of E and the probability of F, find E or F. This is an or. So I'm going to add them together. Probability of E plus probability of F. Oops. So this is 0.4 plus 0.25. There's no overlap, so this is 0.65. The last thing here we're going to talk about today is the complement of an event happening. So the complement means if we look for the probability of something happening, the complement is what's the probability that it doesn't happen. So if P is the probability of something happening, the complement of P is 1 minus P, which is the probability that something doesn't happen. All right, so we got a couple examples on the last page here. So in example 8, it says the local news on the weather report says that the probability that it rains tomorrow is 40%. So the probability of rain is 40%. What's the probability that it will not rain? So that would be the complement, which is the probability of no rain, which is 1 minus 40%, which is 60%. Simple. All right, now this next one is not so simple. All right, so here we are looking at the probability that in a group of 10 people, at least 2 have the same birthday. Assume that there are 365 days in a year, because it could be a leap year. And we want to find the probability of that in a group of 10 people that 2 have the same birthday, or in a group of 23 that at least 2 have the same birthday, or in a group of 30, what's the probability of 2 having the same birthday? Now, if I'm thinking about 10 people, and each of them having a different birthday. So we're going to go about this as, let's find out the probability that they're all different, and then do the complement of that and look for the probability that somebody, 2 people would have the same birthday. All right, so we're going to find the probability of not sharing a birthday. And then find the complement. All right, so if we have 10 people and everybody can have a birthday out of 365 days in the year. So there are 365 ways for the first person to have a birthday, times 365 ways for the second person to have a birthday, times 365 ways for the third person to have a birthday. So basically, this is 300, I'm going to do this up here, 365 to the 10th power. That's the number of possible ways. But if we want them all to be different, that means this first person would be 365. But if they have a birthday on March 10th, then the next person only has 364 days to be different. And then we have 363. And then 362, and then 361. Okay, and we're going down to 10. We need 10 numbers. 6, 5, 4. I need 5 more. So 360, 359, times 358, times 357, times 356. All right, so I have 10 ways to have, or 10 people, and everybody has a different birthday. So here, order matters. So this is a permutation. So what we're really looking at here is the probability, or a permutation, of 365 different days, and I'm choosing 10. And it's a permutation instead of a combination because order matters. Okay. Now, if I'm finding the probability, these are that they're all different, and the probability or the number of possible outcomes was 365 to the 10th power. Now, on my calculator, don't look at what I have above here, but basically, if I did 365, choose 10, and this is a permutation, I'm going to go to Math, and on decimals, you just go to Stat in your function menu, and I'm going to probability here, and I want a permutation. Trying to zoom in here. So Desmos is very similar to this. So in my permutation, I want 365, and I want to choose 10 at a time. Okay, and then I want to take this number and divide it by 365 to the 10th power. This will tell me what the probability is that everybody has a different birthday. And if I do this, the probability that everybody's birthday is different is 0.883, which is the probability of all different birthdays. Now, if we want the probability of somebody having the same birthday, then we got to subtract this from 1. So this is the complement, which is 1 minus 0.883, which is I wrote this down. It's a 0.117, or 11.7% that somebody has the same birthday, that two people share the same birthday. All right. Now, if I am doing this is part A. Now I'm changing my group. I'm making my group bigger. Instead of 10 people, I have 23 people. So I'm still going to do the same calculations, 365. This time I'm choosing a group of 23, and this would be 365 to the 23rd power on bottom. All right, so because I want the complement of this, I'm going to kind of zoom in because I did these before. I started with 1 minus. This is showing that I want the complement, and I want a permutation of 365 and 23. 365, choose 23, order matters, and I'm dividing it by 365 to the 23rd power, and I get 0.507. So this is 1 minus the probability is 0.507, or 50.7% chance. Oops, I'm gonna. And for this last one, now I'm making the group even bigger. I'm going to have 30 people, like in a normal class. What's the probability that 2 people in the same class have the same birthday? So if there's 30 people in my class, I'm going to start with 365, choose 30 over 365 to the 30th power. And if I do 1 minus this probability, I'm going to get, and that's what I have on the second row here, 1 minus that probability is 70 point, or 0.706, which is 70.6%. All right, so this one was kind of difficult, but if we think about people not having the same birthday, now we're looking at a permutation, and we could calculate that dividing by the number of possible ways. All right, so that was a little bit difficult, but I think for the rest of it, you guys should be good. This is probably the only thing that was really new out of all of this. All right, so that's it with probability.